Hello, welcome to Applied Physics and Chapter 15, where we've been talking about magnetism. And with magnetism, we've first discovered the properties of magnets, how they're controlled by things called fields, which basically expose invisible forces. Some things react to these invisible forces, which would be magnetic. Some things don't react to these visible forces, or invisible forces, and those are called non-magnetic. And these fields emanate from the magnet, and the strength of the magnet determines how much things interact with it. We also talked about the source of magnetism, and really there are two sources. One is permanent magnets, where all the atoms, all of the crystals, and all of the domains are lined up so that it creates a strong enough magnetic field. So those are permanent magnets, and those are mostly made of iron, nickel, or chromium. And then you have electromagnets, which are made by a current running through a wire around a piece of iron, and that induces a magnetic field. And you've got the right-hand rule where you follow the arrows of the coils, and that will tell you the polarity of the electromagnet. And then today what we're going to do is we're going to talk about the background of magnetism and how the magnetic fields affect our everyday lives. Everything from how we navigate on Earth to what other planets look like to what stars use magnetic fields for. Okay, so the magnetic field of the Earth. As early as 500 BC, people discovered that some naturally occurring materials such as lodestone and magnetite have magnetic properties, and they would make compasses or other ways of navigation. The reason why compasses were so helpful is because you had a fixed point of reference. When you're traveling, everything moved. The landscape, it seemed like the stars, it seemed like the sun. It was very difficult to make sure that you had a single point of reference. With a magnet, you had a single consistent point of reference that would work no matter if the sky was cloudy or not. And that allowed people to travel during the night as well as the day or when it was cloudy. And that basically doubled your travel time, which allowed you to cover more distance in a shorter amount of time. By 1200, explorers from Italy were using a compass to guide ocean voyages beyond the sight of land. Again, that fixed point, no matter if it was sunny or cloudy or day or night. And that really did bring about kind of the age of exploration. Magnetite. Magnetite, a magnetic mineral made of iron oxide, has been found in bacteria and the brains of birds. Tiny crystals of magnetite may act like compasses and allow these organisms to sense the magnetic field of the Earth, again allowing them to orient themselves in a very large and big world. So Canadian geese may base their migration patterns off of how the Earth's magnetic field is based off of. Other animals have said to have this impact too. Many scientists think maybe whales use it to some degree. Other migratory animals like monarch butterflies also may use magnetic fields to help guide them on their trip from North America to the southern tip of Mexico. Well, we know that Earth is a magnet, and when you use a compass, the northward pointing end of the needle points toward a spot near, but not exactly at the geographic North Pole. And as we've talked about with the PhET lab, the geographic North Pole is actually the magnetic South Pole. Okay? That means the magnetic South Pole of the planet is near the North Geographic Pole. So if this was the United States, this would be the North Geographic Pole with the South Magnetic Pole. And then this would be the South Geographic Pole with the North Magnetic Pole. I'll draw your attention to these spinning things right here. We're going to talk about that later on. So this is how a compass works. The north end of the compass is attracted to the South Pole. The south end of the compass is attracted to the North Magnetic Pole. Okay, now, even with that, magnetic north and true north geographically are a little bit different than each other. Because Earth's geographic North Pole, true north, and magnetic South Pole are not located at the exact same place, a compass will not point directly to the North Geographic North Pole. The difference between the direction the compass points and the direction of true north is called magnetic declination, and that varies about 2.5 to 5 degrees depending on where you are located. Magnetic declination and true north. Depending on where you are, the compass will point slightly east or west of true north. The difference between the direction of the compass points and the direction of true north is adjusted using a ring on the compass. So with our compasses, that orange ring inside, we'll alter it a little bit to shift it. And again, we'll talk about in class how to actually use a compass. Because you don't always follow the needle, you follow where you're supposed to go in relationship to the needle. So the compass is always pointed outwards. You don't always just go north. After correcting for the declination, you rotate the whole compass until the northward pointing end of the needle lines up with 0 degrees at the ring. Large arrow points to the direction you want to go. So maps often list the declination for an area. On the bottom or on the top or on the side, it'll tell you. To go north, you walk in a direction 16 degrees west, the direction was pointing. So that's where that adjustment comes in handy. Okay, so how does the Earth get magnetism? The planet Earth has a magnetic field that comes from the core of the planet itself. So you've got the North Pole and the South Pole. Here's the core. Studies reveal that earthquake waves reveal that the Earth's core is made of hot, dense molten metals. Huge electric currents flowing in the molten iron produce Earth's magnetic field. Actually, let's go back one. See this right here? Here's our molten metal. I remember we've talked about currents in a wire. There's molten metal moving around inside that core. And as the molten metal moves, you've got electrons moving too. And those electrons shifting and going faster in some points in the positive charge beside it create those kinds of currents. So the Earth is really more like an electromagnet than a permanent magnet. The Gauss is a unit used to measure the strength of a magnetic field. And the magnetic field of Earth is weak compared to the ceramic ceramics around in the classroom. So you need to be careful. You can't really trust a compass if there's other magnets nearby. Also, like large deposits of iron will also throw it off. So explorers have gone astray just because the magnet's been pointing to a deposit of iron instead of the North Pole. So be aware. However, Earth's magnetic field is changing. Just like the shifting of the currents inside the Earth, it's shifting enough that the magnetic field is shifting enough. So if you have a very old map, the declination difference between true north and geographic north might even be different. Today, Earth's magnetic field is losing approximately 7% of its strength every 100 years. If this trend continues, the magnetic poles will reverse sometime in the next 2,000 years. So 2005, 2004, and 2000. So it's shifting around a little bit. And notice where our North Pole is versus our magnetic North Pole. All right, like Earth, other planets in the solar system also have magnetic fields. In the case of Jupiter, the magnetic field is very strong compared to the Earth and was mapped by the Cassini spacecraft. That's one of the reasons why spacecraft couldn't get too close, is because all of the electromagnetic waves they were sending back to Earth would have been disrupted by the large field that was occurring in Jupiter. Also, stars have to have a magnetic field. They have molten metal inside them. It's moving. And these magnetic fields can cause sunspots, cause solar flares. And these solar flares can actually affect our Earth because these flares come out and the Earth has a magnetic field that protects us. But sometimes these flares have enough power to get through, and you'll notice satellite disruptions, cell phone reception disruptions, and you'll also notice the northern lights. The sun's uneven rotation twists its magnetic field lines, creating the unevenness here. Every so often, the magnetic field lines snap and become so twisted and reconnect themselves. So that's why you see those solar arcs or those solar flares. This sudden change causes huge solar storms where great eruptions of hot glass flare up from the sun's surface. And the solar storm cycle is usually every 7 years or so. And scientists can predict that. And then finally, magnetic resonance imaging, or MRIs, use magnetism and the different rates of the tissues to figure out what's actually going on in the body. So magnetism is used for medical purposes too. Okay, this is the end of the magnetism unit, and we've talked about the applications and source of magnetism. Thank you. Bye.